Starting a new topic on exponential and logarithmic functions. An exponential function is a function where the variable is an exponent. So whenever the variable is a power, or I could say the power is a variable, something that can change, you have an exponential function. We've seen linear functions that graph as a straight line. We've seen quadratic functions that graph as parabolas. We've seen all kinds of different polynomial type things, even square root functions, x to the 1/2 or square root of x, which isn't a polynomial, but these all behave kind of fundamentally different than an exponential function does. So let's just graph the basic parent function. Y equals 2 to the x is your parent function, because you can't really get one any simpler. If you had y equals 1 to the x, well, for whatever x is, this would just come out to 1. That's actually the same as the line y equals 1. So y equals 2 to the x is considered the parent function here. If I plug in a 0 for x, I'm doing 2 to the 0, and 2 to the 0 is 1. That's the point 0, 1. And if I plug in a 1 for x, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, and 2 to the fourth is 16. It's doubling each time. As you go negative, remember 2 to the negative 1, the negative power just flips a fraction over. It's actually a half. And 2 to the negative 2 is actually a quarter, and 2 to the negative 3 is actually an eighth. It's like 1 over 2, 1 over 4, 1 over 8. It kind of goes in an opposite pattern. And we have this. Well, had I kept plugging in negative numbers, had I plugged in like negative 4, we would have got a 16th. At negative 5, we would have got a 32nd. Whatever I plug in as a negative number, this direction of the graph will keep getting closer and closer to 0, but it will never actually touch 0. And it's an example of what's called an asymptote. An asymptote is a line that your graph gets closer and closer to, but never actually touches. In this case, there's an asymptote at the line y equals 0. Right here is a big, long asymptote. It'll look like the graph touches it because it just gets so close you can't really tell the difference, but it actually doesn't. Now, an important thing to recognize with exponential functions is that the rate at which they increase is always increasing. And it's increasing at what's called an exponential rate. It just keeps growing faster and faster and faster, because in this case, things are always doubling. Whatever this base is indicates how quickly you're growing. That's why it's called growth term, or the growth rate. I think it's just called your growth rate. If you have a multiplier in front, so here is a graph of y equals 2 to the x. This is the same graph we had on the last page. It's counting by 5s now because we're going to cover more ground. Basically what happens is all of these y values go up by 3. So we used to have the point 0, 1, but now it becomes the point 0, 3. And we used to have the point 1, 2, so it's now the point 1, 6. And we used to have the point 2, 4, it's now 2, 12. We used to have the point 3, 8, and it's now 3, 16. And these are all going to be 3 times as high. The y distance here gets tripled. The y distance here gets tripled, and the y distance here gets tripled, although it doesn't really look like that anymore. So that wouldn't be 2, 4, 8, it would be 24, not 16, excuse me. Should be way up here. Actually, way up here. The y values on the other side are also 3 times as high, but that's not much higher. I mean, instead of 0.5, you have 0.75, and instead of 0.5, you have 1.5. Instead of 0.25, you have 0.75, then a quarter becomes, or an eighth becomes 3/8, however high that is. And the graph's going to go like that. It still has the same asymptote at y equals 0. The asymptote wasn't moved at all. It's just now increasing 3 times faster. To move an asymptote, you add a decay term. In fact, exponential functions work in the same way that everything else we've done in this class works. H and k move things left and right. A is your dilation factor, and if a is negative, it changes, it's a reflection over the x-axis. And now b is a new thing to kind of incorporate. If the b value is greater than 1, the graph has growth, meaning the graph goes up as you go to the right. If the b value is less than 1, the graph has decay, meaning the graph goes down as you go to the right. The asymptote is always at the line y equals k, so the k value moves the graph up or down, and that's what changes the asymptote. And then a is called the coefficient of growth or coefficient of decay, depending on if you have a growth or decay function. It's really your dilation factor. It's also, ignore that last part. If a is negative, the graph goes down. If a is positive, the graph goes up. So we'll do some examples. This has a b value. Well, the a value is 2, the b value is 1/3, the h value is 0, the k value is -4. This has a b value of 1/3, which is less than 1, which means this will be a decay function. It's going to go down as it goes to the right. And doing this by hand isn't actually terribly hard. I mean, 1/3, if I do this one here, 1/3 to the 0 is 1, times 2 is 2, minus 4 is -2. If I plug in a 1, 1/3 to the first is 1, times 2 is 2/3, and 2/3 minus 4 is -3 and 1/3. And 1/3 to the second is a 9th. 2 times a 9th is 2/9, minus 4 is -3 and 7/9. And I don't expect you to be able to graph these super accurately, but like 0, -2 would be right about here. 1, -3 and 1/3 would be right about here. 2, -3 and 7/9 would be right about here. It's going to keep on getting closer and closer to -3, but never actually touch it. As you go in the other direction, though, I'm going to do 2, I'm going to plug in -1 for x. I'm sorry, it's getting closer to -4 without ever touching it. As I plug in -1 for x, this flips the fraction over, so it becomes 2 times 3 minus 4, which is just 2. This is the point, -1, 2. I plug in -2. Negative flips the fraction over, so it's really just 3 squared. And it's 9, 18 minus 4 is 14. So -2, 14. Should be right about there. I can keep going like this. The next one, -3, becomes 27, 54, 50. So -3, 50 is way up here. And had I just graphed it like this, it's going to go like that. Hey, I did a pretty good job. There's again an asymptote here at -4. The line's getting closer and closer and closer to, but never actually touching. It's a decay function because the b value is less than 1, and everything was dilated by a factor of 2. You can also do this in your calculator pretty quickly. Y equals, you gonna work for me, calculator? I think I just broke it, so maybe I did it a little bit too quickly. Yeah, I'm not worried about that right now. You can do it in your calculator, take my word for it. Oh, except for this one we were actually going to do in our calculator, so maybe I'll have to try that. But the point I'm trying to make is even if the numbers aren't all that pretty, you can still just sort of grunt it out. So I'll probably have to pause and try this again. Ooh, maybe we're okay. Here we go. I'm going to do -1.8 times 0.4 to the parentheses x minus 1 minus 6. So when I graph it, I get a pretty good idea of how it's going to look. Here, this is a decay function that's been reflected. Because this was less than when it was decay, and decay usually looks like this, but because the a value was negative, it's reflected, so it's going like this, and then the whole thing was moved down 6 and right 1. And all that looks really messy now. You can barely even read it. You know, there was your function, there was your graph, and you could find points from your table this way. Plug in points for x and for y. They're not pretty, but you just graph them and you make it work. Finally, given a graph, we're going to write an equation. There's an important thing to understand about exponential graphs. If you don't have this h term, it's a very poorly written h. If that h term isn't there, then generally graphs contain the point 0, 1. In fact, I guess I should also worry about this k. If there's no h or k, every exponential graph contains the point 0, 1. or at least 0, 0a, I should say. I should phrase this differently. It contains the point 0a. Because when you plug in a 0 for x, you just get y equals a times 1, which is y equals a. So if the graph hasn't been dilated at all, I'm sorry, hasn't been translated left or right or up or down, and you can tell here because the asymptote is 0. If the asymptote is 0, that means that the k value is 0. And we're going to assume that the graphs aren't translated left or right because that actually doesn't happen very often. There's not much need for that. The point 0, comma a is pretty much present in the vast majority of these exponential problems. So you can start with your formula, y equals a times b to the x. We know in this case that our k value is 0 because the asymptote is at 0. So we now know that our a value is 5 because this is the point 0a. If we plug in a 0 for x, we get out a 5 for y. So a must be 5. So I can take my other point here and plug it in and solve for b. I can find that growth coefficient, or that growth value. Now I know b is going to be bigger than 1, because this is a growth exponential curve. So I'll plug in 52.71 for y. And I can plug in 7 for x. And now I just solve this for b. First I divide by 5. And I'm going to do this in my calculator. 52.71 divided by 5. It's 10.542. Keep track of every last little decimal. Don't do any rounding in this chapter ever. And by that I mean just leave that decimal stored in your calculator. And I'm not going to type back in 10.542, but to get rid of this 7th power, I'm going to take both sides to the 7th root to undo that 7th power. And remember, I could also just take my previous answer and do it to the 1/7. That's the same thing as doing a 7th root. And the b value is really 1.4. The fact it's coming out to not exactly 1.4 is because this number right here was actually rounded when I first wrote it down in the first place. So we actually have the equation y equals 5 times 1.4 to the x. If you want to check it real quick, y equals 5 times 1.4 to the x. It's going to give you that same curve. You can check your table and see if you have the same points. At 0 we get out 5. I'll plug in 1.4. I'll change my table set to ask. And at 1.4 we get out that number that it's 7 point, that's 7, that was silly of me, I'm sorry, plug in a 7, you get out 52.7. So thank you, that one was not my smoothest video, but I think it gets the job done.